The planet has so many places to explore, and you never know what you're going to find. This feature is certainly one of the most interesting ones I've ever seen. It's big too, at about 2 miles wide. It almost feels like you're peering into the eye of the Earth. When I saw this, I had a flood of questions come into mind, and I'm sure you do too.
Hello, I'm Myron Cook. Boy, it's good to be outdoors. You know, many of us don't have that opportunity to get outside. Here in Wyoming, it's January. It's a bit cold, but I can tolerate it. And that brings me to Google Earth. I used Google Earth, that amazing tool, to find this eye, this crazy eye in Azerbaijan. And you know, when I found it, I was nearly as excited as you would be as if you had been hiking out and stumbled upon it. So it's a lot of fun. I would encourage you to try to do that and do your own exploring. Now for the fun part. Together, we'll figure out what it is and the seemingly impossible way it formed.
Let's get started on this learning adventure. I think it'd be helpful to look in the surrounding area and see if we can find some clues. Here's another wild-looking feature just 4 miles to the east. And adjacent to it, we see 2 more fascinating features. This is getting more interesting by the minute. I'm looking for what they have in common. Of course, we see that they all have circular shapes, but notice that they have these concentric rings as well. Also, we see this light-colored, almost white material in some of them. This one's interesting. It's sitting on a large hill or mound. Here's yet another one, and I think this one provides a very important new clue. What do you see? I'm focused on these patterns here where it clearly looks like something's been flowing. There seem to be many lobes of blue-colored flowing material. This sure makes your imagination run wild, doesn't it? There are so many of them out here. I'm sure you have some thoughts on this interesting example. This example reveals even more critical information. It sure looks like a volcano with blue lava coming out of it, doesn't it? It's not small either. It's about 900 feet tall, and there's another one nearby that's over 1,000 feet tall. Some context that I think could be helpful. The Google Earth imagery enhances the blue colors that we see. In reality, the natural colors are more like we see here in this older image from Google Earth.
These are sure some interesting features, aren't they? And I know you're thinking about what they might be. It's fun to do that. And some of you probably already know what they are. But I also want you to imagine what you would see if you could see them in person up close. And I'm going to show you some photos and videos and give you some information that'll make it very obvious as to what they are. But I want you to stick with me after this. Don't check out, because we're going to see where they occur across the world. And more importantly, we're going to learn how they form. And let me tell you, when you learn that, it's just as amazing as this great blue eye that we see. So let's get started on this.
On the ground, we see mud, lots of mud, and it's often bubbling away. It looks like it's boiling, but it's not. The highest temperatures recorded in these are somewhere around 117 degrees Fahrenheit. The bubbles are composed of methane gas, and the mud is highly variable in its water content, but it can be up to 70% water. These mini volcanoes are called gryphons. A nice example from Italy, and this one's from the Salton Sea of California. The pools of mud that don't build up into the shape of a gryphon or a volcano are often referred to as mud pies for obvious reasons. So our mysterious eye is a giant mud pie that's 2 miles wide. Unbelievable. And of course, this is referred to as a mud volcano. In fact, all these mud features are often referred to as mud volcanoes. The country of Azerbaijan is the mother lode of mud volcanoes. There have been over 500 identified, and it covers a large area. Interestingly, the small islands along the coast are mud volcanoes. The blue and red dots on this map show most of the main features.
It turns out that I have kind of a fun connection to mud pies. At least it's kind of funny now. So many years ago, when I was working on my bachelor's degree at University of Wyoming, we were learning how to map the rocks out northwest of Laramie, Wyoming, some 40 miles. In fact, it was just off of Interstate 80 near the Wagon Hound exit. And we were wandering around doing our thing, and suddenly behind me I heard the loudest, most terrified screaming you can imagine. Well, I wheel around and take a look, and one of the guys had accidentally stepped into one of these mud pies and was frantically trying to get himself out of it. And he did quite quickly. He was in mud, oh geez, almost up to his armpits. But he got out and he was just fine. I'm sure he thought he was going to go under and be gone. And I did too. But if you think about that, it wasn't going to happen. The density of mud is high, much higher than water, so he wasn't going to go down. But he could have, in theory, if he were alone, he could have gotten stuck and got trapped there. And also, kind of an interesting thing is they had dried over the top, so they were hard to see. So I really can't blame him for not noticing it and stepping on in and having that panic attack.
Examining the Google Earth image of the geology mud trap, I noticed that it's been fenced in. I guess too many geology students have stumbled into it. Turkmenistan is home to some impressive mud volcanoes. Just south of these, in Iran, is a very interesting one. Pakistan is a great place to see mud volcanoes. There are about 100 of them along the coast. In fact, there was an island that was created from one off the coast and then disappeared through erosion shortly thereafter. This one is about 330 feet tall and has that characteristic blue to bluish green color. The color comes from reduced iron within some of the clay minerals. When the mud is erupted and exposed to the air, it is oxidized and turns to a regular old tan color. It's really quite beautiful, isn't it? This particular one is considered sacred by the local Hindu population. A wonderful example of blue mud volcanoes in Romania. They're even found in the deep waters of the Gulf of Mexico. In fact, it's highly likely that most of the mud volcanoes in the world are offshore. Who would have thought that mud could be so interesting and beautiful, especially in the form of these volcanoes and associated features? But we're still wondering why or how did they form? I hope you've been thinking about that. I'm sure that many of you are thinking that there are similarities to artesian springs like this one in Thermopolis, Wyoming. Here we see water flowing up to the surface from underground, not unlike the mud we've seen flowing up from below.
I think we need to talk about springs a bit more using the whiteboard to evaluate this idea. This is a cross-sectional view, so let me draw a tree here, make sure we understand that. I'll put my old tree right here. So we're looking sideways. We've got the ground surface here with the tree growing on it, of course, rising up on this mountain, we'll say. And within here is a layer of rock, of sandstone in this case. It could be a limestone. Sandstone or limestones are pretty common for a water aquifer. But anyway, a layer of sandstone that sweeps down and comes up to the surface here. Now the recharge area for the water, the rain that's coming down, is getting into this layer of sandstone and filling it with water. And let's say the water level is clear up here. Well, that builds up a pressure gradient. There's a hydraulic head here and pressure builds up. There's restricted flow too, which I'll come to here in a minute. But then we have an artesian spring with water just flowing out on the surface. Now I've kept this to a very basic level so we understand these core concepts of a spring system. There are a lot of complications that could come into play. I mean, we could have a fault that cuts down through here, through the ground, and intersects this sandstone, and the water comes up the fault. So we wouldn't even need sandstone in that case to come to the surface, as an example. Or maybe there's a fault higher in the mountain, or a fracture or whatever, where the water can come out there and come out the side of the hill. Maybe the sandstone or limestone turns and breaks out at the side of the mountain, for instance. And we can have small hills that have springs, relatively small hills, instead of a big mountain like we have, etc., etc. But there are two things that all these springs have in common. The recharge area is higher than the discharge area, and the aquifer is confined to some degree, enough confined to maintain a little bit of that pressure so that you have water flowing in an artesian fashion. Now that we have this basic model in our minds of artesian water flow, we can think about, does it apply, or parts of it apply, to artesian mud flow? Do we have any critical questions or maybe concerns? Where's all the mud come from? That's what I'm thinking of. Well, maybe you could come up with the idea, you sit there brainstorming when you think about this, and I can imagine geologists doing this when they first encountered these mud volcanoes. Maybe there's some badlands out here made of shale, and when it rains and you get these gully washers down the washes full of mud, and it comes across this sandstone aquifer just like the water does, and comes down and through to the surface, and that's how you could do it. It doesn't take long to reject that idea. There's a major problem there. With the clay and the mud and whatnot, it's not going to flow through these tiny little pores in a sandstone or in a limestone. It would plug it up immediately. It's impossible. Well, how do we make this work? You know, the more I think about it, I don't know if any of it applies to artesian mud. That puts us right back to square one.
Returning to Azerbaijan, we need to think about this system a bit more. We now feel confident that there is no recharge area like spring water or something that's feeding these mud volcanoes. Therefore, we have to assume it's coming directly from underground. But how deep? And doesn't it seem likely that all these features are being sourced by one giant pool of mud or something underground? How could that be? It turns out that indeed they are sourced by one gigantic pool of mud, and it's deep underground, very deep indeed, at 15 to 30,000 feet. In 2001, when I first started working the geology of the Gulf of Mexico, I learned that there can be giant pools and/or lakes of mud far underground. I literally couldn't get my head around it. It seemed utterly impossible. Let me use this beautiful cross-section of the Appalachian Basin to show you how it seems so impossible to me. Let's imagine that we can look at some sandstone here with a microscope at about 25,000 feet deep. The sand grains are closely packed together with some pore space between the grains filled with salt water. In reality, at these depths, there would be a lot less pore space than I show here. The process of compaction and cementation steadily reduces the porosity or open space filled with water. This basic situation applies to other rock types as well, such as limestone or shale. I might also note that in very rare circumstances, the pores are filled with oil or natural gas. The key point I want to make is that the vast weight of the overlying rock is held up by these sand grains. The rock provides strength to support this great mass overhead. I couldn't imagine a great gap between the layers of rock filled with mud. That means that all the mass, all the weight of the overlying layers is sitting on mud, which is very weak like water. That's like an elephant stepping on a water balloon. Of course, that would create tremendous pressure on this mud. And also what's interesting is that it can be thousands of feet thick. In fact, in Azerbaijan, it's 6,000 feet thick or more.
I have a piece of paper here that's going to help us understand this whole system and how it works, believe it or not. This represents a particle of clay. Now clay is very platy and or sheet-like I have on this paper, and the width of it, say of this, or the radius of a piece of clay, is about 1,000 times larger than the thickness. And I actually did that for this printing paper. And that's what we have with clay. And now we're ready to go to the whiteboard. And now to my rather simplistic drawing here. We have the ocean here with the waves. I even put a fish here. It's kind of fancy. And these lines here represent these particles of clay that are drifting down through the water column towards the floor of the ocean. Keep in mind, these are microscopic. They're measured in width, in the microns, and in the thickness in the nanometers. So they're very, very small particles. And they build up on the ocean floor. And that's what I represent here. All these flat sheet-like clay particles just building up. And in general, they're pretty darn horizontal. And also the white space in here, all the white space is water. So the mud at the bottom of the seafloor, if it's clay-based anyway, mud, is typically 70 to 80% water. So wow, very high water concentration. And these particles just keep raining down, building up a layer of mud. So through time, you continually build up thick layers of rock on top of this mud that was mud. And it could be sand or limestone, and things just keep building up and burying this. Now, if you think about these clay particles, these plates, they just get flatter and flatter, and the water is being squeezed out through time. And this can take a very long time, actually, and a lot of burial. Let me show you something. I have here a sample of shale. It came down from about 9,000 feet down, so it's been buried deep. It's dark colored because it has some organic material in it, about 6% or so. And I'll tell you, it's hard, it's quite strong. And believe it or not, there's still about 5% porosity or so within it, a pore space, and it has water in it. So it didn't get all the water out as it was buried. Now back to these great lakes of mud that are buried deeply under the ground. What I've described so far here doesn't allow for that to happen at all, does it? But there is a special condition. And to talk about that, I'm going to add some layers of rock here being deposited, all this sediment being deposited, but under this special condition, it's being deposited very rapidly. So this thickness is building up, geologically speaking, in a very rapid fashion.
The uplift of mountains, especially those that contain a lot of clastic materials such as sandstones and shales, are a common way to introduce abundant deposition in the nearby ocean.
And that creates disequilibrium because the water can't escape quickly enough out of this mud because it has this shale in it. If you think about it, these shale particles are very platy and they're laying in there quite flat, and that impedes vertical flow. And so it normally happens very slowly. But with this high sedimentation rate, you create a situation the water just can't get out of there. This situation is incredibly unstable because all the mass of this rock isn't resting on more rock. It isn't resting on something strong. It's resting on fluid, mud, and that puts a lot of pressure on that mud. And it can build up to extreme levels. For instance, at about 15,000 feet of burial depth, like we see in Azerbaijan, you get pressures that are nearly 11,000 psi. And when it gets to that level, it can literally break right through all the rock. The pressure is so great, and fracture right up through, or build a conduit up through the rock to the surface with this mud flowing up through there.
It's important to note that the generation of hydrocarbons as oil or natural gas can also increase the pressure.
So I've changed my drawing here a bit and added this conduit or fracture up to the surface, building this mud volcano. And an interesting thing happens. When it initially ruptures, you can have very large volumes of mud come out to the surface in just one big flow. But then as the pressure drops down here a little bit, this conduit or fracture will close back up. It heals itself. And that allows for pressure to build along through this mud work its way to here, build up the pressure again to the level where it reopens the fracture or conduit, and you have another flow, and so on. So it just keeps going for a very long period until you come back to equilibrium.
With the knowledge we now have, we can feel confident that the white material in these rings is from the evaporation of the salt water mixed within the mud. It's salt. There are other ways for mud features to develop, especially in volcanic areas like we see here in Yellowstone and in Iceland. The mud pie that my fellow geology students stepped in was caused from a spring up along a fault that had come into shale near the surface. I won't get into the details of how these mud features form, but they generate very small volumes of mud. Early on the morning of May 29, 2006, near the Indonesian city of Sidoarjo, the unthinkable happened. A mud volcano began to spew mud which quickly enveloped homes, roads, fields, and factories. This is the first high-resolution Google Earth image of the area taken just about 4 weeks after the initial eruption. This mud volcano would be named Luzi. Looking more closely in this area, we see just how devastating it was to many homes. And as you might expect, it wasn't going to end here. More devastation was to come. The center of the volcano is here, and the plume of what looks like smoke is actually primarily steam with a little bit of methane. This small, isolated, dry area is a drilling pad for a gas well that was being drilled at the time. Many scientists believe that it caused the eruption to occur. Others believe it was triggered by a magnitude 6.3 earthquake that occurred 2 days prior 175 miles away. Zooming out on this first image of the disaster taken, I've drawn a heavy red line where they were to be building levees or berms to hold back the mud in the future. 4 years after the initial eruption, we see that the levees have been completed and massive amounts of mud and water have filled in. Going back to the first image, we now realize that everything within the red heavy line, the levees, has been completely destroyed. Heartbreaking. What a disaster. 7 years after the initial eruption, and it's still going, building up tremendous volumes of mud that have broken through the levees on the right side of the image. This image from 2017, some 11 years after the initial eruption, paints a very dire picture. They had to add a levee here. The overpressured mud is surprisingly shallow. The top of it is only at about 1,200 feet down, and the base of it is at 6,100 feet. So that makes it very thick at 4,900 feet. Unfortunately, such a huge layer of overpressured mud suggests that this could be erupting for many, many years to come. I might also mention that much of the mud and water has been channeled out to the river here. The most recent image shown here, acquired in 2025, suggests that things are quieting down. Let's hope that continues.
I hope you enjoyed this video, and if you did, it would be helpful to me if you'd subscribe. Thank you for watching.